What if you could write a compiler that hand builds every weight in a transformer from scratch, with zero training? What if you could write a compiler that hand builds every single weight in a transformer from scratch with absolutely zero training? That is exactly what a developer named PhysicsRob set out to prove, and the result is a project called TorchWrite. You define a computation graph in ordinary Python, and TorchWrite produces the exact weights of a transformer that executes that graph. The output is a standard Phi-3 architecture checkpoint that vanilla Hugging Face loads with no custom code and no trust remote code. Every weight was computed by the compiler, not learned by gradient descent. The project started from a deep question: what sort of algorithms is a transformer even capable of expressing? Most research asks what a transformer can learn from data, but PhysicsRob wanted to separate expression from learning entirely. The approach is elegant in its simplicity. If you can calculate the exact weights necessary for a transformer to implement an algorithm, then the architecture can express that algorithm. And the question of training never enters into it. It is a Feynman-style principle. If you can create it by hand, you understand it. Literally constructing weight matrices by hand would not be feasible for anything complex. So the plan was to define primitive operations that can be easily expressed in transformer weights, then compose these primitives into increasingly complicated algorithms. A compiler then decides how to allocate the residual stream to all intermediate values and figures out where in the various weight matrices each operation belongs. The first decision that mattered more than any other for making the problem tractable: the compiler does not start with a transformer anyone would recognize from a model card. It starts with the simplest substrate possible. FFNs with ReLU as the nonlinearity, a custom position encoding, and no normalization layers at all. A decoder-only transformer in shape, but with every part chosen for compilation convenience. Pushing it to a standard architecture comes later. The first thing the compiler has to manage is memory, and the residual stream is the only shared memory there is. Think of it as a whiteboard with numbered columns. Every value the graph computes owns a set of columns for as long as anything downstream still needs it. A sublayer can only add to the stream, and that one fact drives the entire compilation scheme. A new value lands in zeroed columns because 0 plus new equals new. A value that nothing needs anymore is cancelled by writing its negation, which frees its columns for reuse, and the graph additions are implemented on the skip connection itself, costing no extra columns. Concatenation is logical rather than physical. Every operation compiles down to concrete weights living in attention heads or rows of FFN sublayers. The ops come in three families. Linear operations include add, subtract, and concat. Attention operations let you latch a value at a marker position, read a fixed offset back, or compute argmax and argmin over positions. Nonlinear operations include compare, select, and multiply. The nonlinear ops are built from the transformer FFN activation function, so choosing an activation means choosing your entire op library. TorchWrite provides two implementations. The ReLU module constructs every nonlinear op from ReLU sublayers, and the SWIGLU module constructs the same ops from gated SWI GLU sublayers, which is what the Phi-3 output uses. A graph imports from exactly one, and the compiler rejects a graph that mixes them. A scheduler assigns every node in the graph to a specific layer. The default Optimize 0 places nodes using a heuristic, but Optimize levels 1 through 3 use a constraint programming solver from Google or tools that minimizes layer count. Compiling even a non-trivial example takes under 10 seconds on a laptop CPU. The result is a directory with safatensors, config, and tokenizer that loads like any transformer's checkpoint. For example, the binary increment example parses a binary string and increments it with carry propagation included, producing an ordinary Hugging Face checkpoint that runs with vanilla pipeline text generation. The idea of hand-built transformer weights is not new. RASP defines a language whose primitives map onto transformer sublayers, and Tracker compiles RASP programs into actual weights. Reusing Tracker was not appealing because the RASP language was not particularly intuitive. TorchWrite differs at both ends. Programs are arbitrary computation graphs written in ordinary Python, and the target is a stock architecture. The compiled computation is packaged as ordinary transformers checkpoints in Phi-3 architecture. AutoModel for Causal Language Model loads them with no custom code and no trust remote code. The community reaction on the machine learning subreddit has been thoughtful. One commenter wondered about injecting frozen tools into a network, allowing static complex computations that do not need to be relearned multiple times throughout the network and do not need to be stored in VRAM. Another pointed out that separating learned routing from deterministic operations would make the trade-off much easier to measure. Someone else noted it seems useful especially for smaller models and suggested hybridizing the custom weight model with a trained model. And of course, someone brought up Sutton-Bitterlesson. Several people suggested writing a scientific communication or tech report to describe the approach more formally. What makes Torchwrite genuinely interesting is that it gives us a new way to think about what transformers can do. By hand-building weights and bypassing training entirely, it proves that the architecture itself is capable of expressing complex algorithms, not just learning them from data. It is a proof of concept that opens up a whole new space of possibilities. If you can compile arbitrary computation graphs into transformer weights, then the line between neural networks and symbolic computation blurs in fascinating new ways. The repo has 12 runnable examples to get started. Check out the intro post at ood.dev for the full write-up on how the constructions were derived from the ReLU primitives all the way to a stock Phi-3 checkpoint. If you found this breakdown useful, hit subscribe for more deep dives into the tools shaping artificial intelligence research. Drop a comment if you have thoughts on hand-built versus learned weights.